Lights are, we're 7 minutes late getting started. Most of that was my fault. I was doing something at lunch and lost track of time. So, all right. Before we begin on where we left off last time, just a couple of minor scheduling notes that don't affect this class any, but just to let you know. Thursday afternoon at 2. In case you have another class then, there is a faculty meeting right across the parking lot here in the Ethel Hall building. Now, they're not supposed to cancel any classes for it, but I guess if an instructor really feels like he or she needs to be there, then they may, but I don't think they're supposed to. I know I'm not canceling mine. He said in the email this morning not to, if you have class, meet the class. So, but anyway, just to let you know it's going on in case you are looking for an instructor about that time. If we're not in class, we're supposed to be there. Okay, so I don't remember exactly the time. I knew it was right in the middle of my second mini-term physical science class, so no way I could afford to miss a week's worth of material for a faculty meeting. Okay, then on Friday morning, normally I'm on the Birmingham West campus, 8 to 12. This Friday, I've got a doctor's appointment, eye doctor appointment, right across the street here. I thought it was going to be at Eye Foundation Hospital, but they said, no, he's at UAB West on this Friday. So I said, okay, that's fine. I'm right across the street from where I work. So I'll be there from the appointment's at 8:15, and I'll be there, I'm guessing, at least until 9:15, and then hopefully make my way back to the Birmingham campus around 10-ish or so. I might be able to be there a little ahead of that or maybe later. Depends on how long it takes at the office. Okay, and those are the major announcements I know about. Any questions on administrative or academic side of things? Okay, one other sort of, the summer schedule, they've changed everything. Seems like every term this year, they've changed everything. And they've changed it again. They said our classes weren't long enough and in the summer. And I'd never noticed. In fact, I usually get more covered in the summer than I do the other terms because, you know, the classes are actually longer during the day, so there's not as many breaks, you know, to start a new class, like starting late today or something like that. But they say they say the 4-hour class meeting 2 days a week, like this one would be for a 10-week term, 2 hours and 56 minutes, almost 3 hours. Whereas last summer it was, excuse me, 2 hours and 40 minutes, which I thought was long enough, or something like that, maybe 2:20 or something, but it was awfully long. 3 hours. I'm certain I can't keep students' attentions that long, so I'm going to schedule them for 3 days a week, about 2 hours a day. I think that'll be a little bit better. I could do 4 days a week for an hour and a half, you know, around that each, but I think I'd rather go with 3 days a week, Tuesday, Wednesday, and Thursday. And that way, they want a long weekend on either end. They can, Fridays are always off, but then they can have Monday too. So anyway, that's what I'm going to. So I'm having to change everything in summer schedule. So anyway, if you've been looking for that, you won't see it for a little bit, but we are making progress on it. All right. Any other questions? All right. Where we left off last time, we're in Chapter 11, which is vectors and the geometry of space. And 11.3 is the dot product of two vectors, and that leads to a concept called direction cosines. Okay. In space, it's convenient to measure the direction in terms of the angle between the non-zero vector v anywhere in space, so non-zero vector v, and the three unit vectors I, j, and k. Okay? So, let's just say we have this vector coming out here, vector I, going up like this. I mean vector v going up like this. Now, to vector I, there is an angle between that. J, there's an angle between that. And K, there's an angle between that. And that's what this is representing. The vector, the angle alpha is the angle between the I component, the unit vector in the I direction, the x direction, and beta is the one between j and the vector v, and gamma would be the unit vector between k. I don't know why I started sneezing, and now that open the floodgates here.
Is it always alpha goes with I, beta goes with j?
Yeah, that's sort of it. IJK, alphabetical, alpha, beta, gamma. Those are the first three letters in the Greek alphabet. They don't have a C in the Greek alphabet. So alpha, beta, gamma. And that's how they do it. Now, and these are called the direction angles. Alpha, beta, and gamma are the direction angles of V. And cosine alpha, cosine beta, and cosine gamma would be the directional cosines of that. Okay, what does that mean? Well, if you project V onto the I vector, it's related to that. Remember, the dot product of I and V would be I, magnitude of I, which is 1, times the magnitude of V, which is whatever that is, times the cosine of the angle in between. Okay? And the same thing for beta and gamma. So the dot product of those would be that. So the cosine of alpha then would be the magnitude of V would be the dot product of I and V is magnitude of I times magnitude of V times cosine of the angle in between. So the cosine of the angle in between and magnitude of I is 1. So it would be the dot product divided by the magnitude of V, or multiplied. Divided by the magnitude of V. Okay. So, and what is the dot product of those two? Here we go. The dot product of V and I is the magnitude of V times the magnitude of I, which is 1, times the cosine of alpha. That's the angle in between. That's the magnitude of V times cosine alpha. Okay? Now, what is that dot product between V and I, though? That's V1, that's the component in the I direction, times this, plus 0 times that, plus 0 times that. So it's just VI. That is the component of V in the direction of the I vector, in the x direction. And the same with the other two as well. So basically, this then becomes the cosine of alpha is VI divided by the length of V. Okay? VI times the length of V. And it's the same thing true of cosine beta and cosine gamma. V2 times the length of V. That would be V3 times the length of, divided by the length of V. Those are basically the components of your unit vector in the direction of V, right? All right. So here's the three. Cosine alpha is VI divided by the magnitude of V. Cosine beta is that, and cosine gamma is that. So we have those three. And if you added those together, this is the component. This is V divided by magnitude of V, which is the unit vector in the direction of V. Okay, they haven't said that yet, but it is. And that would be V1 over magnitude of VI, V2, blah, blah, blah. And that would be cosine alpha I, cosine beta V, plus cosine gamma. Be cosine beta J plus gamma, cosine gamma K. And because that is a unit vector, the magnitude of that would be 1. So here we have a new trig identity. In space, cosine squared alpha plus cosine squared beta plus cosine squared gamma is always equal to 1. Okay? So the magnitude of those squared is equal to 1. Okay. So here's example 4. Find the direction cosines and angles for the vector, oh, here it is, v is 2i plus 3j plus 4k. Okay? Now, what do we need to do first to do those calculations? Find the direction cosines, so we're going to be looking for, let me get my pen set up, cosine alpha, cosine beta, and cosine gamma. Okay? That's the first thing. Then we're going to figure out what angles they are, and then we'll show that. Now, how do we determine what cosine alpha is?
Find the dot product of V1 and I.
Okay? It's V1. Okay.
Oh,
Yeah.
then we would take V1 over the magnitude of V.
Exactly. So one of the first things we need to do is determine the magnitude of V. And what would that be? It's the square root of the sum of the squares.
Oh, yeah, that's right.
Yeah.
Makes it all positive.
Yeah.
So it would be would be 2 squared
Yep.
plus 3 squared
All right.
plus 4
Okay, which would be the square root of?
square root of 29 square root of 29.
Okay, let's see. 16 and 9 would be 25 and 4 is 29. Perfect. Okay. And then why did we do that? Cosine alpha would be 2 over root 29. Cosine beta would be 3 over root 29. That goes out of Athens, Georgia, by the way. Okay. And gamma, cosine gamma would be 4 over root 29. Okay. That part's done. Now we need to know the angles. Okay. This will require a calculator, guaranteed. Okay. Because basically alpha is the inverse cosine of 2 over root 29.
Probably, we didn't do this one in our head. 1.19.
Okay, is that radians? Yeah. Sounds reasonable. 1 point what?
19.
Okay. And beta would be
.979.
Okay. And
0.980.
what's that?
It would really be 0.980.
980. Okay, we'll go with that.
And is 0.734.
Okay. Now, it says, show that sum of the squares of those is indeed 1. Well, all we have to do is sum these together. That would be 4 over 29, right, when you square cosine alpha, plus 9 over 29, plus 16 over 29. And then we got, that's how we got it. 13 plus 16 is 29, and that sure enough is 1. Right? So that part was awfully easy. The middle part there, we had to actually do the, oh, and surprisingly, they did it in degrees. So let's go back and do those in degrees, if you don't mind. So we'll just compare what we got in the book. Goodness gracious, I'm stiff.
All right, so that would be the 68.2.
Yep, that's what they got.
And 56.
56, you said?
That's right.
56 point what?
0.1.
0.1 degrees. And that's what they got.
And 42.0.
4.0, you said?
Yes, sir.
Yeah. Perfect. That's what they got as well. Okay? And we've already done the last part. All right, let's see how they did it. I think we did it very similarly. I think daylight saving time is catching up with me awfully fast right now. Goodness, I'm dead. All right. First thing they had to do too was find the magnitude of V, because all the direction cosines depends on that. And we found that to be square root of 29, which is exactly what they got. And then you could just write the cosine alpha as 2 over that. And that gave us 68.2 degrees, so they went on and did it all at once. Cosine beta with 3 over root 29, which was about 56.1 degrees, and cosine gamma was 4 over root 29, which is around 42 degrees even. Okay. And those are, of course, the angles between the vector and those standard unit vectors, I, J, and K.
And so what is radian mode telling us? Like, you know,
Okay.
I mean, like degree mode is obvious, but...
Yeah. Well, radian is a ratio. It's not really a unit. Degree is a unit. That's that big, you know, it's very small. Okay. A radian is also an angle, but it's a ratio of the arc length cut by that angle and the radius of the circle that would be the central angle for. And if I were to say make sure I'm saying it right, yeah. If we were doing something with this, as in doing a mathematical, especially a calculus-wise operation with this, if you're dealing with degree mode, then like I was going to say, I think I will go on and say it, taking the derivative of it or the integrating or something like that, if you leave the angles and radians, those familiar things are just what you get. But if you have them in degrees, then you have to do a chain rule on the derivative of the degrees. Where you don't have to do that for radians because that is a ratio, so there's no real chain rule involved with it. So a lot of the formulas, and just one I basically almost alluded to, though I didn't say I was alluding to it, when I said a radian is a ratio of the arc length to the radius of the circle whose angle that's the central angle for it. By that, you can say that angle then is the radius times the angle theta. Okay, because the angle theta in radians is a ratio of arc length to the radius. So that arc length is the radius times that angle theta in radians. But if you're in degrees, it's not. Okay, and then all your formulas that come out of that, like area of the sector, it comes out beautifully if you use radians, but then you have to contort it and everything else to get the degrees to work out because it doesn't work with degrees. So most of the things we do in calculus, taking derivatives, integrating, and just a lot of the other things, unless they're just absolutely from the primary identities, it didn't matter whether you're in degrees or radians, then you have to do a chain rule type operation with it in order to get the right answer. So radians is the natural way to measure angles, especially from a calculus viewpoint. So the degrees we're used to, but radians are the things that fit, that fit so nicely.
So that's why that's sort of why the the degree circle is 2 pi because it's a radius of 1.
Right.
And that makes
I think sort of what you're saying is if you are stuck on the unit circle, so the radius is always 1, then your angle there is in some fraction of 2 pi. To go all the way around, that would be 2 pi, because the arc length of a circle is its circumference, which is 2 pi times the radius. If the radius is 1, that's just 2 pi. So yeah, that is a direct connection with that. It's somewhat equivalent to, not quite the same thing, but almost equivalent to, this is even stronger, when you're dealing with logs, okay? When you're integrating or differentiating logs, if it's that natural log, it just goes according to plan. If you're doing common logs, like base 10 logs or base 2 logs or base any other log except base E, then you have coefficients that you have to deal with because of the chain rule type concept. It's not quite as strong as that, but it's almost as strong. It's just the natural way of doing things without having to relate to degrees. And that's why it sort of surprised me they went to degrees here. Furthermore, the sum of the squares of those would be 29 over 29, which is 1. All right. Now, this was the vector they gave us. Come out 2 on x, 3 on y, and go 4 up. Now, this doesn't look like it's going 4 up, but you realize that is measured from here. So, yeah, it is 4 up. It's just so hard to represent a 3-dimensional anything on a flat board, a 2-dimensional board. it almost, I mean, looking at this one way, this is a short vector that seems to be about 1 in length that way, less than 1 in length this way, and about 2 in length that way. Whereas, no, its length is 29, you know, or square root of 29. So, and that's between 5 and 6. So, but it's coming out of the board, so it's foreshortened, and it doesn't look to be nearly as long as what it really is. Okay. Now, this was a relatively easy problem to do because you're in what I call the first octave. I don't think they number the octaves, but it's where X is positive, Y is positive, and Z is positive. If you were in one of the other octaves, like the one over there, the one back there, the one over here, or the one beneath this one, or beneath that one, or beneath that one, or beneath that one, then you've got one or more of these components are negative, okay? And then some of your angles could easily be obtuse, okay? But the direction cosines will take care of that because if you're between 0 and pi halves, or 0 and 90 degrees, it's going to be positive, right? Yeah, we know that. But if you go anything beyond that, like the X here, that alpha took over to this side, so you're on the negative X side of things here, then that direction cosine is going to be negative, okay? Which means your cosine would have to be greater than 90 degrees because the cosine in second quadrant is negative. So the SIGN signs take care of everything here with your direction cosines. But then on the other hand, since you're doing an inverse cosine to get these, you're only going to come up with positive angles. You won't get an angle that's down there on the thing below. Then you have to add, I think it's still 360 to it to get the angle they're looking for. I believe that's right. But they haven't mentioned that yet. All right. Now that was example 4. Now we're going to deal with projections and vector components, which is leading up to example 5. You've already seen applications in which 2 vectors are added to produce a resultant vector. Okay? Many applications of physics and engineering pose reverse problem, decomposing a vector into some of the 2 vector components. Now they're going back to plane geometry here, not vectors in free space. So they've sort of backed off and gone back because they say of 2 vector components. If you're in free space, it would be sum of 3 vector components. The following physical example enables you to see the usefulness of this procedure. Even though this is a 3-dimensional problem, everything is happening in 2 dimensions, so you can still use this. And this is what you have. Consider a boat on an inclined ramp. Now, I take it you haven't had physics, is that right? Okay, yeah. This is a very standard kind of physics problem. Consider a boat on an inclined ramp as shown in this figure. Now, they don't tell you here, usually you do know the slope of the ramp. We don't know that now. The force F, the force that's pulling the boat up the ramp, is that way. Okay? However, there's a force due to gravity that pulls the boat not just down the ramp, gravity pulls toward the center of the earth. Okay? Now, that creates a little bit of a problem here if you're trying to figure out how much force you need to pull the boat up the ramp. Because what you're pulling against is gravity. And gravity is pulling 2 parts. It's pulling down the ramp, but it's also, and that's this component, the weight in this direction. But the weight in this dimension is the force that the boat is exerting on the ramp, perpendicular force, which means that's the force the ramp is pushing up on the thing. So gravity is pulling the boat down the ramp a little bit, but into the ramp a bigger bit, and that's why, your tires will, when you have the boat on, they'll flatten out a little bit because of that weight. Okay. Now, to come up with how much force you need this way, see, the ramp is pushing up on the boat that's called a normal force perpendicular there, so that will exactly equal W2. The ramp's taking care of that, okay? It's only this component that you would have to calculate to know how much to pull there. And that's going to be considerably less than the weight of the ramp, of the boat and trailer. The force F due to gravity pulls the boat down the ramp and against the ramp, okay? Those two forces, W1 and W2, are orthogonal to each other, and they're called the vector components of F. So you break the weight component into a component parallel to the ramp and perpendicular to the ramp. And that's how you proceed to solve your problem, which is usually how much force you need to pull the boat out of the water. So F is W1 and W2. I prefer W parallel and W perpendicular. Here's how I usually, being a physicist that I am, I call this W parallel, and I call this one W perpendicular. Just so I don't have to keep track of which one's one and which one's two, you know, because I forget things like that. If I know parallel and perpendicular, I visualize it. I see it right there. Okay, but they do W1 and W2. The forces W1 and W2, or W parallel and perpendicular, help you analyze the effect of gravity on the boat. For example, W1 indicates the force necessary to keep the boat from rolling down the ramp. In other words, the force you have to pull it up the ramp, whereas W2 indicates the force that the tires must withstand pushing against the ramp, you know, and the ramp pushing against it. Right. All right. So, I thought for sure they'd do a problem. They are, but they're going to do this first. Definitions of projection and vector components. So let U and V be two non-zero vectors. Most of the time we're not going to mess with zero vectors, but we always have to say non-zero vectors. Moreover, let U be W1 plus W2. Now is that the same as the figure? I guess so. Okay? So this could be F, capital F before. Why they changed it to U, I'm not sure. Okay? W1 now is called the projection of U onto the vector component of U along the direction of V. Okay? And it's denoted by W1 is equal projection in the direction of V of the vector U. W2 would then be the difference between the U here and W1 there, because W2 is, you know, you just do subtract this from both sides. That's called the vector component of U orthogonal to V. Okay? So, here is your vector V. Okay? Here's your vector U. There's an angle theta in between them. So what is the component of U in the direction of V and the one that's perpendicular to V? Okay? Where U is made up of that parallel component and the perpendicular component. Okay. And we're going to do this for two situations, but the formulas are exactly the same. Let's start with theta being an acute angle. So you're in the first quadrant, everything's positive. Okay? Now, this W1 down here is a component of vector U in the direction of vector V. Okay? And you can also picture that as projection of U onto V. Now here's how this is how someone described it to me, and it really makes a lot of sense, what they mean by projection of. Let's imagine you had a very bright light somewhere way, way, way up there. Very bright. So when you shone it down on vector U here, the shadow of U in the direction of V would be right there. If it was directly over U, that's the shadow, or the projection of U onto V. Okay? And then if you had a very bright light from this way shining in, W2 would be projection of U onto the perpendicular vector perpendicular to V. Okay, so this is when the theta is acute here. This would be your projection. Now this is the picture of it. They're not saying how to calculate it. They're just giving you the definition of these projections. Now when theta is obtuse, meaning between 90 and 180 degrees, or pi halves and pi, then the projection would be in this direction. Obviously in the opposite direction of V, so it would be a negative, but it would be along the line of V. Okay, so it's still the projection along that direction. Okay, now if you can imagine this, and this to me is pretty easy. The cosine of this angle theta is the magnitude of W1 divided by the adjacent over hypotenuse, right? So over the magnitude of U. Okay? Now, this W1 would then be in the direction of V, okay, obviously, okay, but it happens to be greater than V because V's pretty short here, V is pretty long. And that is going to be, just thinking, cosine, dot products have to be involved with this somewhere, right? Because they deal with the dot product. Okay, over here, since this is a obtuse vector here, angle here, this is going to be in the opposite direction because the cosine of this angle is negative in the second quadrant, right? All students take chemistry, okay, or calculus, okay? So that would be negative over here, and that's why it's in the opposite direction. The W1 is. W2 will still be U minus W1 because of the way they set up. Okay, so now here is example 5. Yeah, bottom of page 774.
What does the T stand for?
What's the what?
That's the T stand for. All students take chemistry.
Where's this? On this page or the next one?
It was, you just said all students take.
Oh, that's cosine.
T.
Okay. Yeah. All students take calculus or chemistry.
What is
or
the
whatever.
T?
Is what?
What is the T?
T is tangent.
Oh, okay.
Yeah. All trig functions are positive here.
Right.
Only sine and its reciprocal cosecant are positive here. Tangent is reciprocal cotangent are positive here. Cosine and its reciprocal, which is secant, are positive there.
I just wasn't thinking about the T there. I never heard that before.
Oh, you hadn't? Oh, okay. You didn't take it under me, huh? The trigs. Okay, you took it somewhere else. Okay. Yeah, that's what books ago I remember. All students take chemistry was the first one I heard. All state technical college was the next one I heard. And then all students take calculus, which, why didn't we do that to begin with, you know, because most a lot of trig students don't want to take calculus, but why else would they take? Well, I don't know. Okay. So anyway, this is, okay. Oh, and that's what you were asking about. So it had nothing to do with this slide. Okay. Okay. So here's example 5, bottom of page 774. Find the vector component of U, which is 510, that is orthogonal to V, which is 4,3, given that W1, that's the parallel component of vector V, the component of vector U that is parallel to vector V, projection of U onto V, okay? And that is H6, okay? And U, which is 510, is the sum of those two. So we want, what they're asking for is W2, the component of U that is orthogonal to V, and V is in the same direction as W1, so therefore they're asking for W2. Weird way to ask it. Why didn't they say find W2? You know, it seems like that would have made more sense. They had all those weasel words in there, and frankly, because they've got to. Okay. Now, how in the world are we going to do this? Okay. Given that they haven't given us the formula to do it with yet, we're having to come up with our own. My guess is they want us to find the angle first. Okay? Now, how do you find that angle?
First, you need to come up with the magnitude.
Second?
Find the magnitude
Of what?
of U and V.
Okay. So let's see. Why? Okay, I think you're heading in the right direction. Why do you want that?
So that we can figure out what V1 over the magnitude of V and V2 over the.
Okay. Oh, you're going back to cosines. Yeah, and that actually is a good way to do it. I was thinking, because I know which way they're heading with this, this will certainly work too. Do you agree with this? Irrespective of what it is, this is just that the cosine of the angle between these two vectors, let's just call them theta, is equal to u dot v over magnitude of u times the magnitude of v. That was from our dot product thing. So this could give you the cosine of theta. Then we could find out what theta is. Then we could find out the component, vector component of u in that direction of v, and then ultimately find w too. Okay. Kind of a roundabout way to do it, but it's a pretty easy calculation. First, what is u dot v? Second?
30 plus.
Okay, where'd you get 30? Oh, I see. Okay. The something plus 30.
30 plus
20, yes. So this will be 50. Right? That's the dot product. Okay, and then I think you said that we needed the magnitudes, right? So magnitude of u is square root of?
The square root of 5 plus square root of 10. 125.
Yeah, so it's 5 squared, right? Which is 25 plus 100, 10 squared, which is 100. 25 plus 100 is 125. So there's the magnitude of u. What's the magnitude of v?
The square root of 16 plus 9 is 25.
All right, square root of that is 5. Okay. Now, we could have cleaned the u up a little bit and said this is the same as 5 root 5, right? Factor out a 25, and that square root of 25 is 5, and you still got a square root of 5 in there. I don't know if that helps us any. But anyway, now we've got that this is, get out of there, okay. This is 50, that was the dot product, divided by 5 root 5 times 5. Well, 5 will go into 50 10 times, and this 5 will go into 10 twice, so you have something like 2 over root 5. You could write it 2 root 5 over 5, but this is clean enough. Okay. Now, from that you can get what theta is. Well, let's see. Do we need what theta is? let's see. See, what you were saying before, that was alpha, beta, and gamma in 3 dimension. Can we apply that here? I'm not sure yeah, I think we can. If you were to draw this, here is U. I just drew it somewhere here. And this has magnitude of 5 root 5. Okay. That's the magnitude of it. Okay. Vector V is down here. This is V. And its magnitude is 5. Okay. And the projection of U onto V, that's what we're looking for. That'll be your W1. Okay. Now they're actually writing this bold. We had been putting the projections as being scalar numbers. They're actually putting them as vectors, which is fine because they really are. They're vector components of that. And this is the angle theta. So the vector component of this W1, will be the magnitude of V times, magnitude of U times the cosine of that angle, right? So, W1 is 5 root 5 times the cosine of theta. So, W1, which is this thing right up here, projection of V onto U, that's equal to magnitude of U, which is 5 root 5, times the cosine of the angle in between, which is 2 over root 5, which sure enough is 10, which is that. Now, I think that just happens to turn out that way now, because you see, that's the Y component, and we really, so this is sort of coincidental that that's 10. That's not anything relevant that it's 10. It's just coincidental. Okay. So there is the projection of W of U onto V, and that would be your W1, which is 10. So it's 10 units. It's exactly twice the magnitude of V. It happens to be. Just because of the problem they have here. Okay. And here is it. Okay. Okay. Now, you've answered the first part of it. Now, the second part is, that wasn't even the first part. That just gives you the W1. Now it's saying what is the vector component of U that is orthogonal to V, given that W1 is a projection of that, and U is the sum of those two vectors. Okay? Now, yeah. W1 has a magnitude, by the way, this is the magnitude of W1. We should have put that in. Okay. It's the magnitude of U times the cosine. So it's definitely going to be a magnitude. Okay. Now, as I said, that's exactly twice the length of this one, which I'm sorry, I didn't even read this well. We have just done what they wanted. Yeah, I'm so sorry. They gave us this. I'm sorry. I was calculating this. Okay? All they want us to do here is subtract. I'm sorry. It's not hurting anything, but I am so sorry. I really wasn't. I don't know where my brain is today. Let me take some of this out of here just so you can read it better. Okay? And I'll get that out too. I don't think we really need it. Okay? What they said here, I'm so sorry. They said find the vector component of U, which is sure enough 510, that is orthogonal to V, 4, 3, given that W1, which is projection V on the U, is this vector. Okay? And U is that one. So if that's W1 and U is the sum of those two, all they wanted you to do was subtract W1 from U and get W2. That's all you had to do. That's all you had to do. So W2, that's what they're asking for, is equal to U, which is 510, minus W1, which is 86, and that's a simple subtraction. What does that give you? I am so sorry. What we were doing was absolutely correct, but I thought they were having us calculate that projection. I didn't see they had given it to us. What would that be?
That would be negative 3, 4.
Got it. Okay. Perfect. That's all we had to do in this one. But notice what we were doing was absolutely right. We had said that the W1 was exactly twice V, and sure enough, twice V is 8, 6. So we were doing it exactly correctly, and I just didn't realize until I saw that, wait a minute, they've already given us that. That's all we had to do here. Sorry about that. La, 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 la. Okay. And let me clear this out of the way. Any questions on that? It didn't hurt everything else we did, but it was totally wasted time. They gave it to us in the problem. And here's what they do. Because U is W1 plus W2, and W1 is parallel to V1, is parallel to V, it follows W2 is the vector component of U orthogonal to V, which you get by subtracting. W2 is U minus W1, which is 510 minus 8 through 6, which is negative 3, 4, which, by the way, has a magnitude of 5, just like we've done before. And here's Catherine. All right. Okay. You know, there was one other thing I forgot to say at the beginning of class. I'd been saying it every time and completely forgot it this time. We have just passed midterm. Last week was midterm, sometime around Tuesday midnight. And they usually ask for midterm progress reports sometime shortly after midterm. And trying to see this. 4 of the 7 people in the class have turned in something to me. So if they ask, you are passing at midterm, the other, what did I say, 5, 1, 2, 3, no, 1, 2, 3, I can't add. No, I said 1, 2, 3, 4 have turned in something, the other 3 have not. So the other 3. So if you can get me something soon as you can, then it's not going to make a bit of difference because no one does anything with them anyway, except you might get bugged by people emailing you or calling you saying, do you need some tutoring or do you need, counseling or something like this? So that's the only deal, but just to let you know that. All right. Now, continuing at example 5, here's what we've got. Here they drew it out. Here's vector U, 510. Vector V over here is 8, 6. No, I'm sorry, 4, 3, vector V. and then they did the component of vector v in the direction of u in the direction of v, and we found out that was H6, and they told us that, okay? Now, just to point something out to you, because we're doing everything from the origin, these are points, but they correspond to the components of vector. U would be angle bracket 510, V would be angle bracket 43, W1 would be angle bracket H6, and W2 pointing in that direction, perpendicular to V, but the other component of this would be negative 3/4. I would just assume they're putting in the coordinates of the points, which happen to be the components of the vectors as well, because everything's measured from the origin. Okay. Any questions? Sorry, I started off doing way more than that problem required. All right. Because I was already mentally heading this way. The projection using the dot product, if u and v are non-zero vectors, then they've got to be non-zero vectors. Then the projection of u onto v will then be, this looks awfully close to what we just had, the dot product of u times v divided by the magnitude of v, okay, and then multiply that by the vector v. Well, this is a magnitude, that's a magnitude. When you multiply it there, it becomes a vector. Now, let's see, what in the world does that say? Okay. Now, first place, if you were to take one of these magnitudes here in the denominator and move it under the v here, right? Then that would be a unit vector in the direction of v, right? Now, what would you have left? You would have left u dot v up here. U dot v is magnitude of u times magnitude of v times the cosine of the angle in between. Well, this magnitude of v will wipe out the other magnitude of v down here, and you would just have the magnitude of v times the cosine of theta, which is exactly what we were doing, giving you that component in that direction, in the direction of the unit vector of v. So, yeah, this definition makes sense. Now, how in the world do you remember something quite that wacko? Here's my little trick. And this is just a trick, okay? This is a vector v, that's a vector u. Well, I'm going to use v dot u. It doesn't matter or you dot them at all. So that's where you get your numerator. But this one's sort of suppressed. That's a subscript, right? So I'm going to put the magnitude of v down here, okay? In here, and then just remember that leaves you the unit vector v over, the unit vector in the direction of v over magnitude v here. So there's one way I kind of remember how to get all the pieces in there. The projection of u onto v can be written as a scalar multiple of a unit vector in the direction of v. That's what I just said. Okay, sorry, I didn't realize I was going to say it. Take out one of these as a unit vector in the direction of v. This is just a scalar multiple. What is it the scalar multiple of? Exactly as I said, it's going to be magnitude of u, magnitude of v times the cosine of the angle in between. Magnitude of the v's goes out, magnitude of u times the cosine of the angle. The scalar k is called the component of u in the direction of v. So that's the dot product of u dot v over magnitude of v, because these cancel out, then you're left with magnitude of u times the cosine of theta. That's really what I was carrying through on the previous thing before I realized they had already done it for you, but I hadn't told you how they got it. Is that wobbly illumination, or is it my eyes? Okay, good. I'm so glad. I was thinking I need to see the doctor this week, earlier. All right, so here's example 6. That is the next one. Find the projection of u onto v and the vector component of u orthogonal to v for this. Three-dimensional vector. Here's u, 3i minus 5j plus 2k. V is 7i plus j minus 2k. Okay? So first, what is the projection of u onto v? Can you tell me that thing? This is projection of vector u onto vector v. Formula we just had, anyone remember what it was?
The dot product of u and v.
U dot v over
the magnitude of vector, of v
squared, and then you go
call that
times v. Perfect. Okay? Because it's going to be a vector, and that's why you need a vector in there. So let's do the math here. What's the dot product of u and v?
Dot product would be
21.
Negative 5.
Yep, that would be 16.
And negative 4.
Yep, 16 minus 4 would be 12 divided by magnitude of v. Got to do that one now. Magnitude of v would be what? Square root of
The square root of 9
right?
plus 20.
Wait. Where'd you get 9?
I'm looking at u.
I'm sorry? Oh, you're doing u. Okay, no. Magnitude of v.
That would be 49
Right?
plus 1
Okay, that'd be 50.
plus 4.
Yep, that'd be square root of 54. Now, is there anything we can get out of that? 4 won't go into that. 2 will go into that 27 times. Oh, but 27 is, that's 6 times 9 is 54, so that'd be 3 on the square root of 6. That won't help us. Well, it does too. So we'll do 3 on the square root of 6, right? 9 times 6 is 54. So 3 will go into 12 4 times. So it'd be 4 over root 6. Okay? And that's going to multiply by the vector v. So basically what that is 28 over root 6i, right? Plus 4 over root 6j minus 2, minus 8 over root 6k. I believe I did it right there. Yay or nay? Goodness, that thing will drive me crazy looking at it too long. Eyes go weird. See what we did? We just multiplied this thing 4 over root 6 times each of those. 28 over root 6i plus 4 over root 6j minus 8 over root 6k. All right, so there's the projection of u onto v. And it says, and the vector component of u orthogonal to v. What would that be? It's what we were calling our W2, I believe it was. And what was that?
Is W1 plus u.
Yeah, W1 plus W2 is u, so u is this minus W1, and that's your W1 there. I'm going to call that projection, okay? So this will be 3, I'm going to write it in this notation if it's okay. 3 minus 5, 2 minus 28 over root 6, comma, 4 over root 6, comma, minus 8 over root 6. Okay, the big boo hiss here is that we've got root 6's in the denominator there. So we're going to have to multiply this by root 6 over 6, this is by root 6 over 6, that by root 6 over 6. And then see what we get. We get 3 root 6 over 6 minus 28 root 6, 28 root 6 over root 6. So that's going to be 3 root 6 minus 28. Over root 6, right? I'm not sure this is how the book is going to do it. But then you have minus 5 root 6, minus 5 over root 6, minus 5 root 6 over root 6 minus 4. That would be minus, no. I'm doing something really stupid here. Let me go back and erase this one. Okay. This is 3 root 6 over root 6 minus 28 over root 6. Yeah, that's right. Okay. I did it right. Okay. And this will be minus 5 root 6 over root 6 minus 4 over root 6, and this will be 2 root 6 minus 8 over root 6. Okay. Now those are weird ways to write the numbers, and something's not looking very good here. Oh my goodness gracious. Here I have it. It's root, that thing squared. I thought, we're not supposed to have all these root 6's in here. Okay. Whoops. Supposed to have my eraser running. Okay. Sorry about this. I was going to say, this is a weird. Okay. I think I could have left some of that, but I'm just going to erase it all. It's just such a mess. Okay. Because what this is magnitude squared. So magnitude of V squared is 54. Duh. Okay. So let's see what we got now. U is that, and the projection here would be oh, we're multiplying that. This would be okay. All right, let me erase some more here because I'm having trouble seeing. Okay. This would be $21. I've already done this. Oh no, okay. The numerator, if my memory's right, was 12. Is that right? That was 21. Yeah, pretty sure that was right. 21 minus
that's 5 minus 4.
minus 5 minus 4. That's minus 9. So, yeah, that's 12. 12 times V, the magnitude of V. No, 12 over this. 12 over 54. And 12 over 54 would be 2 over 9. Right? So this would be 14/9. I'm going to write it in this notation. 2/9 and 4/9, negative 4/9. Let's see if I got that right this time. 14/9, 2/9, and negative 4/9. Got it. Okay, and then 4 times, or U times that, U minus that projection. Okay, U is 3, 5, 2, 3, negative 5, 2. When we put that over 9, that would be 27/9. This will be 45/9. And this would be 18/9. Right? Yeah. Okay. So 27/9 minus 14/9 is 13/9. Okay, this is much better. Minus 45/9 minus 2/9 is minus 47/9. And minus 4/9, no, 18/9 minus a minus 4/9 would be plus 4, it would be 22/9. So there is our W, I sure hope. 13/9 I minus 47/9 J plus 22/9 K. Yes. Dumb. Okay. Now let's see how they did it. Hopefully a little bit cleaner than what I did. If not, we change books. Okay. Projection of U onto V is this U dot V over V magnitude squared of V times V. So that would be 12/54, exactly like we got after a while, times that, which is the same as 2/9. So 2/9 times 7 is 14/9 I plus 2/9 J minus 4/9 K. Ah, there's Brian. All right. We're doing projections, decomposing a vector into vector components, doing projections, that kind of stuff. So that, and this is example 6 on page, about the middle of page 775. And I apologize that the projector is doing weird strobing-like stuff, so it's driving me nuts. Okay, so there is your W1, which is your projection of U onto V by this formula right here. Okay? This is a symbol for it. Okay? We got that by the dot product of U and V and the twice the magnitude of V. So it's not the square root of, but the sum of squares of 7 squared plus 1 squared plus negative 2 squared would be 49, 50, 54. So that's your denominator. The numerator is the dot product of those two, which is 12, and that reduces to 2/9. And then you multiply 2/9 times vector V, and you get that. Okay, now that's the first part. We haven't got it into the vector component orthogonal to V, so then you subtract that W1 from U. So that was 3I minus 5J plus 2K minus 14/9 I plus 2/9 J minus 4/9 K. And they didn't tell you how they did it, but basically make this 27/9 I minus 14/9 I, and that would be 13/9 I, minus 45/9 J minus 2/9 J, that would be a minus 47/9 J, and that would be 18/9 K minus 4/9 K minus a minus, which is plus 4/9 is 22/9. Okay. Done. Now, let's go. Oh. Here's the figure, if you find this helpful. All right. Now, they've changed their axes around some. Here's X, there's Y, and there's Z. Okay? So minus 3I, that would be 3, be right about here, 2, 4, 6. So 3 would be this way. Positive 3I minus 5J, that would be back this way, 2, 4, 5 would be here. So that gives you that point there, and then plus 2K, which would be up that high from there. So there you have the U vector. The V vector over here, which they don't show anymore, here it is. Okay, 7I, which would be out to here, plus J, 1 in this direction, and then a minus 2K. So going down 2 from there, and there you got that. So there you're over in that octant there on that plane and projected above it. This octant here, this isn't your positive, this is your positive. No, this is your positive octant here. Your first octant here, but it's below it, so it's whatever the one is below there. And you're wanting to find the projection of U onto that V. And they show you approximately the perpendicular nature here. There's no way I can graph that in my head and know which is perpendicular, because the dimensions are just really wacko here. So that's what you got. So this is your W1, and subtract that from U and you get W2. Because notice W1 is fairly small, smaller than U or V, either one. V is actually a pretty good sized vector here because of that 7I. Okay. So the previous one, the projection was longer than V. This one, the projection is much, much shorter than V. Okay. Work! Okay, never mind. That's the next topic. Let's back up and do example 7. I'm going to back way up right there. And we'll do projection 7 here. It's not quite the same picture, but it's awfully close. Okay. A 600-pound boat. That basically is your force downward. So this is 600 pounds. That's the magnitude of that force downward. Okay? Sits on a ramp inclined at 30 degrees. This angle here is 30 degrees. Actually, I think this picture is closer to reality than that one. The one in the book looks like a 45-degree angle. So I think this one's actually closer. Okay? As shown in this figure. What force is required to keep the boat from rolling down the ramp? So in other words, you want to know the force here you're having to do to keep it at this position and not let it roll back down the ramp. Okay. Now, what we're dealing with here is we break this force component into two vectors. One, they're putting W1 this way and W2 that way. Now, I don't care which way you number them, letter them, or something like that. I like to call them W parallel and W perpendicular. That, to me, says a lot better than me. To me. Okay, now, this is not drawn to scale, not to this scale either. That angle is less than 30 degrees. Okay, but at least it's better than the other. Now, if this angle here is 30 degrees, okay, here's a horizontal, there's vertical, okay? This line is perpendicular to the horizontal, and this line is perpendicular. It's perpendicular to the ramp, is what I was going to say, but that sort of makes no difference. Here's what I'm going to do here. I hope you'll find this not too bad. You see this angle here? That is our 30 degrees, right? That little angle there, okay? And if this is your 90, well, there's the 90 degree angle here. That would make this angle up here what? That angle right there is 60 degrees. Because this little triangle here, this little light of mine, okay, there's the adjacent, there's the opposite, and there's the hypotenuse. And this is 30, that has to be 90, right? But this line here is perpendicular to that one, and this is 60, so guess what this one has to be? That's your 30 again. So this is 30 degrees here too. All right. Now we've got a right triangle we can play with, okay? Because we know the force down this way, 600 pounds. This component is going to be adjacent side component. This will be the opposite side component. Does anyone remember what the opposite side component was for a 30 degree angle compared to its hypotenuse? Please say yes. In other words, what's the sine of 30 degrees? Pi 6.
Sine is...
This is not drawn to scale, so don't use this to try to, as a prompt here. What is the sine of 30 degrees or sine of pi 6? 1/2, exactly. So that means this component down here is exactly 300 pounds, okay? And this component right up here then, and that would be the same as that one. This one on the here, who cares what it is, but that would be root 3 over 2 times 600, which would be 300 times root 3. But we really don't care about that. All we're interested in is know how much force it's going to take to keep that from rolling down here. Well, this is being pulled down by a force of 300. That means this would be a force of 300 as well. Does that make sense? Okay. Let's see how they did in the book. Oh, they did projections and sines and cosines and all that kind of stuff. And did they ever? Oh, yeah, there it is. The magnitude of the force is 300, so force of 300 pounds is required to keep the boat from rolling down the ramp. Exactly what we got. And they did it sort of the same way. Okay? Now, are we running out of time?
I'm not sure.
Yeah, 14.
We got what?
14 minutes.
14 minutes. Okay, I thought we had some time left. So, the word for you today is?
Projection?
Work! Okay, so let's move on to work. The work done by a constant force F acting along a line of an object, boy, that's a strange way to say it, along the line of an object, is given by magnitude of force times the vector magnitude PQ. Now, why they even introduced vectors into this, I'm not absolutely certain. Because the force is in the same direction as the vector, that is just force times the displacement. That's what work is. but they're magnitudes, okay? The force acts along the line of the motion. So this would just be the magnitude of the force times the magnitude of the displacement, and that would be the work done. By the way, the units for this would be Newton meters, which are joules, or pounds, which is your force in the U.S. customary, times feet, and that would be foot-pounds. Okay? Either one, whatever you happen to be using. Okay? Now, when the constant force is not directed along the line of motion, you can see from this figure that the work is done by the projection of F onto the line PQ, and that would then be the projection of F onto that. If your movement is from here to here, that's your displacement. Your force is up this way, so it's only this component of the force that is doing any work on it. Okay? The component up here is not. That's just relieving some of the friction between the surface and the box. That's just reducing that, but it's not doing any work in that direction. So it's the projection of F in the direction of the motion times the magnitude of the motion. Well, what is that projection into the direction of the motion? If you remember, okay, this projection here would be that times the cosine of theta, that is the projection in this direction, times PQ. Well, that magnitude of F times the magnitude of PQ times the cosine of the angle, that's just simply the dot product between the two vectors. So as before, we used to have to remember a formula, we have to use the angles and stuff. Now, if we know the force vector and the displacement vector, it's a simple dot product. You don't have to worry with cosine angles anymore. Now, if you need them, yeah, you still worry with them. But here, it's not asking you that at all. Okay? So there is our new formula. Work is the dot product of the force times the displacement vector. Okay? So the notion of work is summarized in this definition. The work done, and by the way, work is a scalar quantity. Force is a vector quantity, displacement is a vector quantity, but work is a scalar quantity. Work done at W by a constant force F at its point of application moves along a vector V is one of the following. See, the work is the projection of F onto PQ times PQ. That's projection form. The work is the dot product of F and PQ. That's the dot product form. Okay? Because this projection includes the cosine of the angle, the magnitude of F times the cosine of the angle. When you get it in there, you got that. Okay. Any question? All right. Let's do, is example 8 the next one? I believe it is. And let's find the work. To close a sliding door, a person pulls a rope with a constant force of 50 pounds. I sure hope that's easier to see. Okay. All right. It's not particularly clear to me, but, oh, there's an arrow. I was wondering, what in the world is that? Here's the force that he's pulling. There's an angle of 60 degrees here, and he's walking along that direction. Okay. To close a sliding door, a person pulls a rope with a constant force of 50 pounds at a constant angle of 60 degrees as shown in this figure. Find the work done moving the door 12 feet to its closed position. Okay? Now, obviously, we do know the magnitude of the constant force, 50 pounds, but that really, you could break that down into component forms, but then on the other hand, why should you? I mean, how would you find that? The work done by moving the door 12 feet to its closed position. And there's the 12 feet that the guy is moving. See, I would put him right next to the door pulling that way. They have them way out here, and it doesn't at all seem to be right, but it's okay. Okay. So what would be your definition of work? Work is not a vector quantity, it's a scalar quantity. Well, the way they've shown the problem here, we want to do the projection form. Projection of the work I'm sorry, not work, force. Okay. Projection of the force in the direction of the displacement, which is PQ. Okay? That we're going to multiply by the distance, 12 feet. Okay, that's the formula we just had, the projection form, projection of PQ, of F onto PQ, times the magnitude of PQ, which they told us was 12 feet. Okay? Now, what is the projection of force onto PQ? Well, that projection is the force, constant force of 50 pounds, so that would be 50, or F, times the cosine of 60 degrees. So you want the force that's parallel the distance that way. That is your projection. Okay? So this will be 50 pounds times the cosine of 60 times 12 feet. All right. Anyone recall what the cosine of 60 is? 1/2 again, because the other time it was sine of 30, they're complementary angles. So that'd be 1/2 of, I'm going to do 1/2 of 12. That'd be 6 times 50 is 300 foot-pounds. Usually I write it the other way. 300 foot-pounds of work. Okay? Half of 12, 6 times 50, 300. Okay, hopefully they got that too. Yep. And let's see how they got it. They use in the projection, we can calculate the work as follows. Projection of PQ of F onto PQ times the magnitude of PQ. And that would be a cosine 60 times the magnitude of F times the magnitude of PQ. That would be 1/2, 50 times 12, which is 300 foot-pounds. All right, and that does finish the end of this section. Goodness, I'm running out of energy. Daylight saving time is killing me. Homework exercises here. Do any of the odds 3 through 9. They all should be at Calc Chat. 3 should be at Calc View. Do any of the odds 11 through 17. They should all be at Calc Chat. 13's at Calc View. Do number 19. It's both at Calc Chat and Calc View. Do any of the odds 21 to 29. They should all be at Calc Chat. Sorry. Either 27 or 29, they should both be at Calc Chat. I'm sorry. Any of the odds 31 to 35, they should all be at Calc Chat. 31's at Calc View. Any of the odds 37 to 43, they should all be at Calc Chat. 37's at Calc View. If you want to explore concepts 45 or 47, they should be at Calc Chat. And then 49 should be at Calc Chat. Do either 51 or 53. They should both be at Calc Chat. And I'd say any of the odds 55 to 59 should be at Calc Chat. I'd say 61, sorry. 55 through 61 at Calc Chat. Then do 63, it's a true-false problem. Then 65, it's a sort of a standalone type problem. And then 69 is approved. 71, so bond angle, 73 and 75 are both proofs. And by the way, there is that 75 talks about the Cauchy-Schwarz inequality, and that's something 2 or 3 potential paper topics right there. All right, do we have time to get started in 11:4? Okay, yeah, okay. We end at 10 after? Is that right? Or 20 after? 10 after, yeah. All right. So we'll begin next time at 11:4. Okay. What's that? Okay. Why am I doing that now? I should be doing this.